Hello everyone. Let me start with a simple thought. How do chemists keep track of electrons in reactions where oxygen and hydrogen are not directly involved? Imagine water forming from hydrogen and oxygen. 2H2 gas plus O2 gas gives 2H2O liquid. Here, hydrogen goes from oxidation number 0 to +1, while oxygen goes from 0 to -2. This change in numbers helps us decide which element is oxidized and which is reduced. Oxidation is defined as an increase in oxidation number and reduction as a decrease. So, oxidation number is like a bookkeeping system. It allows us to follow electron transfer even in covalent compounds where electrons are only partially shifted.
To make this practical, chemists develop a set of rules. First, all elements in their free state have oxidation number 0, like sodium solid, chlorine gas, hydrogen gas, or oxygen gas. Second, for ions, the oxidation number equals the ionic charge. For example, sodium ion is +1, magnesium ion is +2, chloride ion is -1. Third, oxygen generally has an oxidation number of -2, but there are exceptions. In peroxides like H2O2, each oxygen is -1. In superoxides like potassium superoxide, oxygen is -1/2. And in oxygen difluoride, oxygen is actually +2 because fluorine is more electronegative. Finally, hydrogen is usually +1, but when bonded to metals like lithium or calcium, as in lithium hydride or calcium hydride, hydrogen takes -1. Fluorine is always -1 because it is the most electronegative element. Other halogens like chlorine, bromine, and iodine are generally -1 too, except when they are bonded to oxygen in oxo compounds. In neutral compounds, the sum of oxidation numbers is 0, while in ions it equals the overall charge. For example, in carbonate ion, CO3 2-, the 3 oxygens contribute -6, so carbon must be +4. Transition metals are especially interesting because they show variable oxidation states like iron existing as +2 and +3, or manganese ranging from +2 all the way up to +7. These variations make them central in many redox reactions. If we look at the periodic table, we see patterns. The highest oxidation state of a main group element is often equal to its group number. For p-block elements, the highest state is the group number -10. For example, group 15 elements like nitrogen and phosphorus go up to +5, while chlorine, in group 17, reaches +7. That's why we find compounds like phosphorus pentoxide, P2O5, and perchloric acid, HClO4, where chlorine is in its maximum oxidation state of +7. Recognizing these trends helps predict what oxidation states are possible for each element. To avoid confusion with elements that have multiple oxidation states, chemists use the stock notation. Here, the oxidation state is written in Roman numerals in brackets after the element name. For instance, iron Ht chloride, FeCl2, contains iron in the +2 state. Iron 3 chloride, FeCl3, contains iron in the +3 state. Similarly, copper I chloride is CuCl, and copper 2 chloride is CuCl2. Mercury is special. Mercury I chloride is Hg2Cl2, while mercury 2e chloride is HgCl2. This notation instantly tells you which oxidation state is present. Let's solve an example. Problem 7.3 asks us to assign oxidation numbers and represent them in stock notation. For HAuCl4, gold is +3. In Fe2O3, iron is +3. In MnO2, manganese is +4. Using this, we write gold the 3 chloride, iron the 3 oxide, and manganese IV oxide. Now, problem 7.4 gives a reaction. 2Cu2O plus Cu2, S forms 6, Cu plus SO2 gas. Here, copper is reduced from +1 to 0, while sulfur is oxidized from -2 to +4. This is clearly a redox reaction, where Cu2O acts as oxidant and Cu2S acts as reductant. These examples show how oxidation number makes redox identification straightforward. Oxidation numbers also help classify different types of redox reactions. In combination reactions, two elements combine, like carbon plus oxygen giving carbon dioxide, where carbon goes from 0 to +4. In decomposition, a compound breaks down, like 2-sodium hydride forming 2-sodium plus hydrogen gas. In displacement, one element replaces another. For example, zinc reacting with copper sulfate, giving zinc sulfate and copper metal. Finally, disproportionation is special. The same element is both oxidized and reduced. A classic example is hydrogen peroxide breaking down into water and oxygen. Here, oxygen changes from -1 to both -2 and 0. Disproportionation only happens when an element can exist in at least 3 oxidation states. So let's summarize. Oxidation number is a powerful tool to keep track of electron shifts, especially in complex covalent or ionic reactions. We assign it using rules. Free elements are 0, ions equal their charge, oxygen is usually -2, hydrogen usually +1, and halogens usually -1. Stock notation makes variable oxidation states clear. Using oxidation numbers, we can easily classify reactions as combination, decomposition, displacement, or disproportionation. This concept is universal and forms the backbone of redox chemistry. I hope this session helped you see oxidation numbers not just as abstract numbers, but as a language chemists use to read the story of electron movement. In the next session, we'll see how to balance redox equations using oxidation number and half reaction methods. Until then, keep practicing. Chemistry becomes simpler the more you play with these numbers.